Hello everyone. In this video, I'm going to explain simple LR parser, that is SLR parser. It is also called as LR of 0 parser. What is this SLR parser? It is a shift reduce parser or LR parser. What is LR? L stands for reading the input from left to right, and R stands for performing rightmost derivation in reverse order. So this SLR parser is a parser that performs bottom-up parsing. Bottom-up parsing. What is bottom-up parsing? It constructs the parse tree starting from leaves and ends at root. So this shift reduce parser, it makes use of input buffer that holds the string to be parsed, and it makes use of a stack, and it also makes use of one symbol, that is a dollar symbol, that is used to indicate the end of the input, and it is also pushed at the bottom of the stack. So this shift reduce parser makes use of a parsing technique that performs mainly 4 actions. Shift action, during which the next input symbol is pushed onto the stack, is shifted onto the stack. It makes use of reduce action. What is done during this reduce action? Find the top of the stack that can be reduced. We call this as a handle. Identify the handle and replace with a correct non-terminal, exact non-terminal. So that is done during the reduce. One more action, accept, during which it identifies that input is valid input and declares that the parsing is successful. Performs an action error, during which it identifies that there is a syntax error and calls error recovery routine so that it can continue with the parsing of next statements. So this is one example about that explains about these different actions. This grammar has been taken for explanation, and this is the input that is taken. So initially stack has this dollar, it is pushed with a dollar initially, and input is terminated with a dollar, and the first action is the shift, during which the first symbol is pushed onto the stack. Then here it identifies that ID can be reduced using this production. F gives ID. Here we say that ID is a handle. So identify the handle that is top of the stack that can be reduced. So here ID is a handle, so replace it with the F. So this is nothing but reduce. So that is what is done here. It is reduced with the F. You can trace with the other actions, and here it has done one more action, that is accept. When this performs this accept action, when it finds that E is on the top of the stack, which is the start symbol, and there are no more input. So these are the different actions that are done by this parser, shift reduce parser. Now we are going to construct the SLR parser. SLR parser. So for this construction, we need all this. Okay, we need augmented grammar. Okay, we need LR of 0 items. So likewise, we have the different concepts we have. We make use of canonical LR of 0 collection of items, and we make use of 2 functions, closure and goto functions, and using this we will be constructing parsing table. So this is the model of the LR parser. So here it makes use of input, stack, and a parsing table. To construct this parsing table, we make use of all these concepts. Okay, so I will explain these with some examples. Here we have one term that is called as a augmented grammar. What is augmented grammar? Suppose if this is the grammar, we add a new non-terminal a dash, okay, and we add a production a dash gives a. So this, after adding this new production, we say that this as a augmented grammar. Suppose a is a start symbol, we add a new start symbol a dash and the new production a dash gives a, and this is called as a augmented grammar. After this, we use LR items. What is this LR item? So item is a production. Item is a production where you will have dot. You can observe here you have dots. That dot may be at the beginning or maybe at the end or maybe anywhere in the body of the production. This is body of the production, you will have a dot. So what is the meaning of this dot? Okay, I will explain with this particular item. Suppose you have a LR parser. Suppose you have an input string. The meaning of a gives x dot yz. It means that the parser has derived the string, string that is derivable from x that matches the input, and yet to see the string that is derivable from yz. That is what is the meaning. I'll explain once again. The meaning of this item is it has seen the strings that are derivable from x that matches the input, part of the input, and it has to perform the derivation of a yz. That is what is the meaning of this item. Particular item that I have considered here is a gives x dot yz. So what is item? Item is a production where it will have a dot in the body of the production. Okay, so then we will have the collection of these items, set of items we say, and particularly we call them as a canonical collection of items. Canonical collection of items means set of items that are unique, and we make use of two functions, closure and goto, to find this canonical collection of items. Okay, let me explain with an example. I have taken one example, grammar. This is the grammar. First we will start with a computing LR of 0 item sets. For this we need a augmented grammar first. This is the augmented grammar. Okay, after that you take this first production. After augmentation, you take this first production, you add the dot at the beginning of this initial of this production, and this particular item we call it as a initial item. So this is how we start. Next, after finding the initial item, you check what is the symbol after the dot. The symbol is non-terminal a. You write all the productions of a, and precede it with a dot. So this is what we have done at the first step, and this set, and this set we call as first set. We number it as a I0, and this we call it as a closure of initial item. We have used the function closure. What is the closure function that it does is, after the dot, checks do you have a non-terminal and write all the productions, precede it with a dot. So in the beginning we have this set. Again you can apply closure, but right now how to apply the closure, you find after the dot what symbol. After the dot we have do we have non-terminal? No, we have a terminal. You can't apply closure on this. You take this item. After the dot, do we have non-terminal? No, we can't apply closure. So here the construction of one set is over. So this is one LR of 0 item set I0. Likewise, we can find other item sets. How to find other item sets? In that case, we have to make use of one more function, go to function. Earlier in the previous slide, I have told that we have to make use of two functions, closure and go to. Closure and go to. I have explained right now what is closure. Let me explain what is go to function. Okay. Now I'll make use of go to function to find other sets. What do you mean by go to function? What that does? It moves dot to the right by one position. You take the first item, move the dot to the right. That's what I have done here. Take this item, move the dot to right by one position. That's what I have done here. Move the dot to right by one position. That's what we have here. Correspondingly, we will have three sets, and I will label it as I1, I2, I3. Okay, and I have labeled here. I have moved a dot after A, moved a dot after parenthesis after A. Okay, now again in this set, can you add few more items? Can you add few more items? Can you add few more items? Okay, so that you have to check. And finding few more items in each of this set, we will apply again a closure function. Okay, what is closure function? Closure function means after the dot, do you have non-terminal? Okay, you see this first item set I1. In this we have this item A dot. After the dot we don't have anything, so you can't apply closure. Okay, move to the set I2. You have one item here. After the dot you have non-terminal. Now you can apply closure. What that closure does? After the dot, if there is a non-terminal, right now we have non-terminal, add all the productions of that non-terminal. Here we have, after the dot we have A, add all the productions of A. You add it here and put a dot in the beginning. Put a dot in the beginning. Add these two here, put a dot in the beginning. That's all. This is what? Applying the closure. Okay. So I have now set I2. Check, can you apply closure again? No. Okay. For this, can you apply closure? Can you apply closure? No. Applying closure means after the dot you should have non-terminal. Right now you can't apply further. So this is the set I2. You can't add any more items to this I2. Okay, move on to the set I3. Set I3. Okay, in I3, can you apply closure? No, because after the dot nothing is there. Here I'll tell you one more thing. The item, okay, where dot is at the rightmost position in the body, we say those such type of items as final item. Final item. Okay, so this is a final item, this is final item, this is a final item. Okay, okay, now so we have obtained three item sets along with the I0, I1, I2, I3. Okay, now we have to see, can we derive few more item sets? Okay, start from I1 Okay, start from I1 and apply go to. Apply go to for I1, apply go for I1, apply go to for I2, apply go to for I3. Same thing what we had done with I0, same thing we have to repeat with I1, I2, I3. Apply go to. Okay, so here we have go to function for I1, I2, I3. Okay, go to means what do you mean by go to? Move dot to the right by one position. Here you can't move dot. Okay, so with the I1 you can't move. Okay, but you check with the I2, set I2, set I2. Can you apply go to? Yeah, you can apply go to, because here dot can be moved, dot can be moved, dot can be moved. So 3 times you can apply go to, like we had applied with the I0. Yeah, go to with the first item, that is moving dot after a, moving dot after parenthesis, moving dot after a. So we have now 3 more sets, 3 more uh, 3 more 3 more sets, 3 more sets. Okay, once we have got the result of go to, check can you have few more items, few more items, few more items. So to find few more items in each of this set, you have to apply closure. Okay, what is closure? After the dot, do you have non-terminal? Right now in this I4 we don't have non-terminal after dot, so you can't apply closure for I4. Okay, so no more items in this set I4. Okay, check can you apply closure with this set. Okay, can you apply? Yeah, you can apply, because after the dot we have non-terminal, so applying closure means add the productions of A, productions of this non-terminal A. So these two productions you add, put a dot in the beginning. So that's what we do here, put a dot in the beginning. So we have these 2 more items, but this set, total set, we will label it as a I2, not I5. Why? Because this set is same as this previously obtained set, so we will label it with the same name, that is I2, I2. Okay, next continue with the I3, applying closure with the I3. You can't apply because dot is at the end. This is final item. For the final item you can't apply closure. Final item means dot is at the rightmost position. Okay, so now in this step we have obtained I4, I2, I3. What is the new set that we have obtained? I4. These two are already existing. Okay, from I4 can you derive few more sets? How to find? You have to make use of go to function. Go to function. Okay, that is go to on I4. Go to on I4. What do you mean by go to? Move dot to the right by one position. That is move dot after the parenthesis. That is written here. Okay, you label this as I5. You, while labeling, you have to be sure that this item set doesn't match with the previously obtained item sets. Now this doesn't match, so you have to label with a new name I5. Okay, now in this set I5 can you have few more items? How to find few more items? You have to apply closure function. Can you apply closure function to this item? No, because after the dot we don't have any symbol. So these are the different item sets. We call these as canonical LR of 0 collection of item sets. Canonical means each set is unique. And here this is nothing but a DFA, LR of 0 automaton. It parser, this SLR0 parser works like a DFA, deterministic finite automaton. And in this we add, you observe here difference, I have added one arrow that is labeled with a dollar, and one that is a accept. What do you mean by this? When the parser is in the I1 state and when it finds a dollar, it declares that the input to the parser is valid and successful parsing. Declare that parsing is successful. Okay, so now one more thing, this dollar and accept you have to write with the item set that contains this particular final item. A dash gives A dot, not with any other final item sets such as I3, I5. Only with this we have to write. Okay, so till now whatever I have explained, that explanation is with respect to this automaton, but while solving the problem, this is for your understanding, but while solving the problem you don't have to write complete sets for all the problems. If it is asked, then only you can write this LR of 0 automaton, but usually we will solve this problem in this method. Okay, how do we start? You write the grammar and you write the augmented grammar. This is the augmented grammar, and write the initial item and apply closure on that initial item and closure. What do you mean by closure? After the dot, if there is a non-terminal, write all its production with the dot in the beginning. So this is what the set I0. Okay, find further sets. How do you find further sets? By applying the go to function on I0. Go to on I0, go to on I0, go to on I0 for the symbol A parenthesis A. What do you mean by go to? Move dot after A, after parenthesis, after A. That's what I have done. And you can give the name as I2, I1, I2, I3. And within these sets, again you apply the closure to find further items. Okay, then in this set, the new set that we have obtained I1, can you get any more item set from I1 by applying go to? You can't apply go to on I1, because in I1 we have item where dot is at the end. Next, can you apply go to on I2? Yeah, you can apply, because go to means move the dot, move the dot, move the dot. So that is what we have here. Go to applied on I2, I2, I2. Go to applied on I2, I2, I2. Same explanation. Okay, and in this new sets, the new derived set is I4. Again from this set I4, can you obtain new set by applying go to? Yeah, you can apply go to, because dot can be moved after parenthesis. Here you can see go to on I4 where dot is moved after parenthesis. That's what. Yeah, dot is moved after parenthesis. Dot is moved after parenthesis. So now we are done with the computing LR of 0 items and the construction of LR of 0 automaton. Now we are going to construct SLR parsing table. Okay, so here this is the parsing table that we are going to construct. Let me tell the various fields. It has action entries, go to entries. Under the action you will be writing all the terminals. Under the go to you will be writing all the non-terminals. Okay, along with the terminals you are also writing dollar also. Don't forget writing dollar. And for every state you are going to have a row. So we have a 0 to state 5. So these many rows you are going to have. Now what about the entries? You can see here I have written S2. What do you mean by S2? Shift to state 2. Okay, then what do you mean by R2? Reduce using production 2. Okay, production 2 means this, production 1, production 2. In the given grammar, I will write all the productions. If there are alternates, separately you have to write and number them. This is first production, second production. That's what is the meaning. R2 means reduce using production 2. Okay, we have one more entry, that is except, that always comes under the dollar. Okay, and for a state that has the final item, particular final item. Which a final item? So this final item, this final item, a dash gives a dot. Okay, so this is actually new production that we had written in the augmented grammar, if you remember. Okay, in the augmented grammar, this was the new production, and if I write a dot after this, then it will be called as a final item. And this final item, wherever it appears, in whichever state it appears, okay, here right now it appears in state 1, so for this I will be writing except under the dollar column. Okay, now I'll tell you how to make entry S2, R2 and all. Yeah, one more. Under the go to, we will be writing only the state numbers. We don't precede it with a S or R. We just write the state numbers. Okay, how to make entries into this state, into this parsing table? For the explanation, simplification of the explanation, I'm going to make use of this automaton. Otherwise, you can make use of that problem solution. Okay, yeah, let me how we have got this S2. Explain about this. You see the state 0. State 0. In this, there are transitions, 3 transitions. If there is a transition for terminals, okay, for example, parenthesis, it is making a transition to state 2, so you have to write it as shift 2. So likewise, it makes a state transition to 1 on A. That's what we write it here, 1. Don't precede it with a S or R. Now, so this is what how to make entries S and under this non-terminals. Okay, now let me explain about these 2 entries. How to make entries for reduce. R stands for reduce. For this, you have to write the productions in order and find the follow of the non-terminals. Right now in this I have only one non-terminal, so write down the non-terminal follow of that non-terminal. So these are the follow of a non-terminal. Okay, now say you you imagine that you have made entry for 0th row, 1th row, 2. Okay, now you are able to make an entry for state 3. See the content of state 3. The content of state 3 is a final item. Okay, what do you mean by final item? Dot is at the end. Item where the dot is at the end. So we have this final item. Okay, so you check what is the production number of that. The production number is 2. Okay, and one more thing that you have to see, what are the follow of non-terminal A. See, for this production, what is the non-terminal on the right side? That is A. What are the follow of that? Okay, see the entries under dollar and parenthesis. Dollar and parenthesis, write as RR, and 2 means what is the production number of this. A gives A, production number is 2. That's what I have, R2. Okay, you just verify why do we have R1 under the state 5. See the state 5, we have a final item. Okay, so you see what are the follow of A. Follow of A is dollar closing parenthesis. Under closing parenthesis and dollar, make a entry RR. Why do we have 1 here? Because the production number of this is 1. That is what? R1. So that's all about entries into this parsing table. Okay, now let me explain about the last part of this problem, how the parser performs various actions: shift, reduce, accept, it is invalid. Okay, and here we are given with the input string, that is a. Actually this is a valid string according to this grammar. Okay, and it has to say that it is a valid. Okay, how does that parser concludes that this is valid? That's what we are going to consider. There is a separate algorithm for parsing. That algorithm you can check in the notes, and I'm going to apply that algorithm. See, for applying the algorithm you have to make these columns. Okay, stack, symbols, input, action. Okay, and you have to make use of this parsing table. You need parsing table. Make these columns. Under the stack you start with the state 0, and under the input you write the given input and ended with a dollar. That's what we start here. This is what we have started. This is first thing that we write, state 0 in given input, okay, with the dollar. Okay, now you see what is the top of the stack and what is the input. First symbol in the input, that is parenthesis, 0 parenthesis. You check out in the table, 0 parenthesis. It says what? S2, shift 2. That is what here it is written. Shift 2 means shift the number 2, and at the same time you proceed with the next symbol. After parenthesis, what is the next symbol? That is A. And the currently scanned input symbol you have to write under the symbol. Okay, continue. Next, what is the top of the stack and what is the current input? Current input is A. 2A. Check the table. 2A. So we have shift 3. That's what is written. Shift 3. So push 3. Then proceed with the next symbol. Write A on the side and proceed with the next symbol, that is closing parenthesis. Okay, 3 closing parenthesis. Check the table. 3 closing parenthesis. We have what? Reduce. So we have to perform different actions. So here it is written as reduce, and particularly it says that 2. What do you mean by 2? Production 2. This is the production 2. So how to perform this reduce action? Here you reduce using this production. Reducing means body of the production has to be replaced by head of the production. Body of the production should be replaced by head of the production. Lower letter A is replaced with the lower letter A is replaced with a capital letter A. That is reduction. Okay, now one more point you have to remember. How many symbols you have reduced? You have reduced one symbol and one top of the stack element you pop. That's what is written. Pop 3. If you pop 3, what is the top of the stack? 2. Okay, that's what we have here. 2 on the symbol that we have obtained after reducing. 2 and A. 2A. So we have what? 4. So that 4 you have to push. So many actions you have to do. I'll repeat it again. When you have a reduce action, check with which production you have to perform. Here the production is A gives A. So reduce that. Under the symbol column, A you replace with the head of the production. How many symbols you have reduced? 1 symbol. Pop 1 symbol. 3 you pop. 3 is no more needed. After popping, what is the top of the stack? Top of the stack is 2. Okay. 2 at A. 2 at A. 2 at A we have 4. 4 you have to push. So this is how we get in the next line. The next line we have 0 to 4 it is. And the currently being scanned input remains the same. It doesn't change. It changes only during shift action. During the reduce action, currently being scanned input will not be changed. It will remain same for the next step. Okay, so now what is the top of the stack? 4. What is the symbol? 4 parenthesis. 4 parenthesis, closing parenthesis. We have what? S5. What do you mean by S5? Shift 5. Shift 5. So we push 5 and the symbol, that scanned symbol, we write it here and we move further. That is, we scan the next symbol, that is the dollar. So this is what is done, shift 5. Okay, now we have the top of the stack 5, top of the stack, top of the stack 5 and dollar, $5. See, $5. We have R1. What do you mean by R1? Reduce using production 1. This is what? The production 1. Okay, production 1 means the body of the production. Body of the production. This is the body of the production has to be reduced to head. In the next line you have to write this is reduced to A. Okay, how many symbols you have reduced? 1, 2, 3. 3 symbols you have reduced. So 3 elements on the top of the stack should be popped. See, 3 symbols you have reduced. So 3 symbols you have to pop. So if you pop 3 symbols, 3 states, you will get the next top as 0, 2, 4, 5 will be removed. 3 symbols reduced. So 3 elements will be popped. You will get the next top. And how do you continue? You have to see 0 and a reduced symbol A. You check the table 0 at A. That you have to push. So this is what we do whenever there is a reduce action. Okay, so now we have 0, 1. We have current symbol as a dollar only that we had in the previous stage. The same dollar symbol we will have now as the currently being scanned input. Now what is the top of the stack and what is the symbol? $1. Check. $1 says that accept. What do you mean by that? The string that is given string is a valid string. So here it declares that, it makes an action that accept. It declares that the parsing is successful and input is valid. So this is how we have to show the actions carried out for a given input string. So this is about the solving problem based on this grammar. Any grammar, if you try the same method in the similar way with the other grammars. Okay, so thank you.